Hello, this is the second part on Laplace transform. Just briefly remember that we're starting with a function f of t defined on the time domain, and we have a definition to compute this Laplace transform that says multiply that function by e to the minus st and then integrate from 0 to infinity, and that will give you a new function we call capital F of s, which is the Laplace transform. So let's work out another example. The identity line f of t equals t, so the Laplace transform of t would be given by the integral from 0 to infinity of e to the minus st times t dt. So we're going to use integration by parts for this integral. So let's think of the variable u being equal to t, and also let's think of dv being equal to e to the minus st dt, which means that v would be, so that means that we want to take that integral being equal to uv, so the integral e to the minus st t dt, this would be u times v, which is minus t over s e to the minus st minus the integral of minus 1 over s e to the minus st dt. Okay, so this becomes, this is equal to minus t over s e to the minus st, then we get a negative 1 over s squared e to the minus st. What we have to do now is evaluate the limits of integration. So in other words, the Laplace transform of f of t equals t becomes minus t over s e to the minus st evaluated from 0 to b minus 1 over s squared e to the minus st, also evaluated between 0 and b, and we take the limit as b goes to infinity. And it's not difficult to see that the first term here becomes 0, and the second term we evaluated b and then obtain this, which means that by taking the limit as b goes to infinity, this first portion is going to go to 0, and then we are left here with 1 over s squared. And this is what we would call capital F of s, the Laplace transform of the identity line f of t equals t is equal to 1 over s squared. So here we're going to find this function, which is stepwise constant. It's defined as 0 for values of t that are negative, and as 1 for t being 0 or positive, and this is the function u of t. So it's not difficult to picture this. We could sketch this function. Here would be the value of 0, right? So here is the function. This is t, and let's say this here is 1. This is 0, and this is 1. So what we'd like to do is to consider a constant that is non-negative. And we consider a shift of that Heaviside function. In other words, consider u evaluated at t minus a, where a is non-negative, and this would be the same values of the function, 0 and 1, but now we have to say the argument is t minus a. Whenever t minus a is less than 0, that means t is less than a, and when t minus a is greater than or equal to 0, t is greater than or equal to a. So that will be shifted in this function. It's the same type of graph, Now we have a number a. Okay, now the function is going to take the values of 0 for all values less than a, and exactly at a becomes a constant value of 1. Okay, again, this is t. So we're going to compute the Laplace transform of u of t minus a, which is the integral from 0 to infinity of e to the minus st u of t minus a dt. And so we're going to break this into the integral from 0 to a, and then from a to infinity. So this would be equal to the integral from 0 to a plus the integral from a to infinity. This is e to the minus st multiplied by the value of u, but remember that function is defined as 0. So this is precisely what the sketch that we have here. The function is 0 for values of t that are less than a. So here's that exponential times 0. And here we have e to the minus st times 1 dt. And so this means that this first integral becomes 0. We're left with this integral from a to infinity, which is equal to minus 1 over s e to the minus st from evaluated from a to b, taking the limit as b goes to infinity. And in a few extra steps, let's see, this will become minus 1 over s e to the minus s b minus 1 over s e to the minus s a. We're taking the limit as b goes to infinity. Which means this becomes 0 plus 1 over s e to the minus s a. So that would be the so-called function f, capital F of s, the Laplace transform of u t minus a, right, which is a shift of this function that's known as the Heaviside function. So one thing that would be convenient at this point is to summarize the calculations of Laplace transforms. Suppose that the function f of t is a constant c, then its Laplace transform is c over s. It could be that this function is a power, f of t equals t to the n, then its Laplace transform would be the Laplace transform of t to the n is n factorial over s to the n plus 1. Laplace transform, if the function is e to the minus at, the Laplace transform is 1 over s plus a. And then we have other examples of very classical functions here. For example, sine of omega t. The Laplace transform of sine of omega t is omega over sine square plus omega square. The function is cosine of omega t. Its Laplace transform is s over s square plus omega square. Then we can include also hyperbolic sine and hyperbolic cosine, and the Laplace transforms are listed for these functions here. And in this table, in this summary of calculations of Laplace transform, we can include the Heaviside function, which turn out to have Laplace transform of e to the minus a s over s. Okay, so This will be convenient to have summarized for what comes next.